Welcome to the second webinar in our series, our spring 2025 webinar series. This one is entitled Introduction to Topographic Point Clouds. My name is Matthew Beckley. I'm a data scientist at OpenTopography, and I'm joined today by Chris Crosby, who is the PI on OpenTopography, one of the PIs on OpenTopography project, and gave last week's webinar. He's going to talk about structure from motion. So I'll pass off to him at a certain point. And we also joined by Chelsea Scott, who is also a co-PI on this project. So just a reminder, last week we did an intro to open topography that was led by Chris. Today we're going to talk about point clouds. Next week we're going to do an introduction to digital elevation models. And then the final webinar on March 26th will be about topographic differencing. All of these webinars will be recorded and on our YouTube channel. So you could always, if you could make this, you could always watch those at a later date from our YouTube channel. Just a little bit of logistics. This is a Zoom webinar, but we have muted everyone by default. So only the presenters can speak. If you do have a question, please use the Q&A option. So Chris and Chelsea will be monitoring as I'm speaking, and so they'll answer some of the questions. We may reserve some of the questions towards the end if they're a little more complicated and are not easy to answer in the chat. And we'll try and reserve maybe like 5 to 10 minutes at the end for questions, so that if there are a little more involved questions, we can dig in a little bit deeper. And last point to remind people is that it's the same Zoom link for all 4 webinars. So in the next couple webinars, you can use this Zoom link to get in. We'll try and send out email reminders, but just in case we forget, you can always just use the same webinar link that you used for this one. So the agenda for today is we're going to talk very briefly, just some very basic Lidar theory, nothing too deep. Then we're going to talk about data collection. Then I'm going to pass it to Chris, and he's going to talk about structure from motion for a little bit. Then we're going to talk about data files and data products from Lidar, point cloud classifications. Finally, we'll just talk about some of the open source tools that are available to users. And then I'm going to reserve a large chunk at the end to actually just do a demo, because sometimes that's really useful to figure out. We'll do things like talk about the open topography landing pages, how to run a point job. We'll do a deeper dive into the 3D point cloud visualizer. And then lastly, we'll talk about how to have bulk access data from open topography. So most people are probably familiar, but just in case, LiDAR stands for light detection and ranging. The actual physics of it is fairly simple. It's basically a pulse of light that's emitted from a laser. That pulse of light travels through space and it intersects an object and is reflected, and then that reflection or that signal is then detected by a detector. And since we know we are measuring the time that it takes between that laser pulse and when it's returned, you know the speed of light, so you can multiply the speed of light by that total time of flight, divide by 2, and you get the distance from your laser pulse to that object. Now, critical to this operation is very accurate clocks. So you have to be able to time tag when that laser pulse was sent out and time tag when that signal was returned very accurately if you want an accurate distance measurement. So the basic physics of it is fairly simple. As you can imagine, things get very complicated depending on laser types, detector types, things like that. But it's operating on the same principles as radar, just in a different wavelength of light, which I'll discuss in this next slide. So I like this graph. This is a graph of the electromagnetic spectrum and its properties, and it's sort of a nice way of visualizing this. So here you have the wavelength and the frequency of all these different electromagnetic radiations. You have everything from very long wavelength radiation, like radio waves, to very small wavelength and destructive, at least to the human body, wavelengths like gamma rays and X-rays and things like that. So as I mentioned, LiDAR and radar operate on very similar physical principles, just they use different portions of the electromagnetic radiation spectrum. So radar stands for radio detection and ranging, because the early radars operated with the radio waves. The more modern sort of radars use actual microwaves, and many of the radar altimeters that are on satellites, they use microwave radiation. And this has a benefit in that a lot of these long wavelengths are not attenuated by weather, so like clouds, fog, rain, things like that. So you can imagine having this on a satellite is really useful because you don't have a whole lot of control over how that orbit is tracking. You can't just avoid weather events. And so having an instrument that can penetrate clouds is much more beneficial. The downside to these radars for altimeters and for measuring topography is that because you have this very long wavelength, that translates to a very large footprint on the ground. And so it's very difficult to sort of discern very fine resolution features because you're averaging all the elevations that fall on that footprint. And so if you want to measure finer scale, high resolution features, this is what the motivation was to move towards LiDAR, to get a more discrete footprint. And so you can get sort of higher res imaging of the surface. So LiDAR, as I've marked off on the spectrum here, stands for light detection and ranging because a lot of it is in the visible spectrum. Most LiDARs, though, are in the near infrared portion of the spectrum. And so that means their footprint is much smaller. And so you can get a higher res footprint, you can discern higher res features. Um, so it's a smaller footprint. The downside is that LiDAR can be attenuated by clouds and water. But this is where it comes into play of sort of tailoring your instrument to what you're studying. If you're studying water or things like that, you can use LiDARs that are in the green channel visible spectrum. This is 532 nanometers, and these LiDARs can actually penetrate water and get measurements from bathymetry and within the water column. You have atmospheric LiDARs where if you're measuring ozone concentration or dust or any other atmospheric constituents, you can tweak your laser wavelength to measure those things that you're interested in studying. So LiDAR is becoming pretty ubiquitous. You can find it on a variety of platforms. Most of the stuff that we deal with at OpenTopography is on an aircraft base, but we do have things like terrestrial laser scanners. So this is that image here where we have a LiDAR scanner on a tripod and it actually spins around and measures surfaces nearby. You have LiDARs on drones now, cars, satellites, as I mentioned, helicopters is a big one with power utility companies. But we're even starting to see handheld devices that have LiDARs. Like this is sort of a tape measure here and an optical rangefinder. And many of you may know that the new iPhone has a LiDAR. And in fact, we did a webinar 2 years ago that discusses how to use the iPhone LiDAR. So I would encourage users to check out our YouTube channel to check out that video. So as I mentioned, most of the data that we have at OpenTopography is airborne LiDAR from sort of low to mid altitude aircraft, but we do have a variety of different data sets. But that's sort of the bulk of what we have. So that's kind of what this presentation will be geared towards. And so this is sort of the basics of what an airborne LiDAR collection would look like. There's three main components that are kind of critical to the whole thing. You have the laser and the sensor. Sensors are otherwise sometimes called a detector. You have an inertial measurement unit, an IMU. This is also referred to as an INS sometimes, inertial navigation system. And then you have the GPS both on the plane and on the ground. And all three of these components are actually critical. The IMU is particularly important with an aircraft collection because as you can imagine, you have this platform that's flying around in space and bumping around with headwinds and things. And so you need to know where that laser is pointing in space and its angles. And that's the job of the IMU. It's recording, it has gyroscopes on it, so it's recording very precisely how that laser is pointing. And and so this way you'll be able to take all of these 3 or 4 reference frames and in the end process them and put them into an accurate location on the ground. And we'll talk about data processing in a couple slides. So I like this slide because it kind of gives you a good visual of sort of what a LiDAR pulse would look like and how it sort of interacts with the topography. So in a very simplified scenario, you'd have an aircraft with a LiDAR pulse shooting nadir, meaning like orthogonal from the plane directly down, intersecting the top of the canopy and returning. But most modern LiDAR systems are not like that. They're not single pulse returns. They're actually like sweeping back and forth or conically sweeping that's what the pattern would be on the ground. So it's interacting with the topography at various angles and different things. And so that changes how that return gets back to the detector. One of the issues you could see here, which I like, is like this LiDAR pulse is illuminating this tree, and you can see there's these shadows on the ground because no energy made it down to the ground. That energy was either reflected back from the canopy or was absorbed or was reflected away from the detector. And so one rule of thumb that I like that I always tell people is that if you're on the forest floor and you look up and you can see bits of sky, any kind of light, the LiDAR return you can get a LiDAR return on the ground from that. So it is pretty amazing what LiDAR can do and where you can get a ground return from. There are obviously scenarios where you couldn't, like very dense tropical vegetation. If you can't see the sky from the ground, then you'd never be able to get a LiDAR return from that. Um, but also another thing to keep in mind is this is one LiDAR pulse. So you have to remember these are overlapping flight lines, and if the LiDAR is scanning at different angles, so these areas here where that are showing shadows, I mean, there's no ground return. That might get from another shot at a different angle, you might get a ground return there. So it would fill in that sort of gap. But this is sort of idealized scenario of a single shot and what it would look like. One other thing to mention is water can be very tricky with LiDAR. Sometimes it can act as a mirror. So if it's very flat and your LiDAR pulse is coming in at an angle, it can act as a mirror and sort of shoot that LiDAR pulse out into space and never returns to the detector. Or if the water is very clear and very flat, the water may just penetrate and not actually get a return. Previous projects I've worked with for high altitude LiDAR collections, we've found that like any kind of a little bit of roughness to the water, if there's a little bit of wind action and the waters are rough, we would get returns. But again, this turns back to my previous point about how you want to tune your sort of the instrument type to what you're studying. So if you really were interested in studying water and bathymetry, you would use a green channel laser, which would operate better and sort of be able to measure things from both the surface under the water to things within the water column. So this just going to talk about a little bit of the evolution of these LiDAR detectors, because this is important to how the elevation measurement is actually returned to the user and what the user sees. So very early on, the early LiDAR systems were a single pulse, single return. So you'd have a shot, maybe it hit the top of the tree and comes back, and that's it. You get one return. And that was great, but it was obviously very limited in what it can do. So this very quickly evolved into a multi-return system. So you'd have a single pulse from the laser, but you could get multiple returns. So you might get a signal from the top of the tree, mid canopy, and ground, all from a single LiDAR pulse. And this is much better. But some of the research communities, particularly in the forestry community, they wanted to characterize the forest and get a better idea of biomass. And so having just these single discrete points wasn't really enough to do that. And so this developed into full waveform LiDARs. And so this plot on the left is sort of describing what a full waveform LiDAR does and what it would look like from an airborne collection. So it's basically treating the entire energy profile as a distribution or a waveform. And so this red line is showing, this graph is intensity versus time. And we're plotting as the laser pulse comes out, you'd see a peak in the intensity. That's the laser shot out. It's going to travel through space and hopefully not intersect too much, but you would see kind of a baseline sort of noise level that you can model out. And then once that pulse starts to intersect the forest in this example, you're going to get a peak in energy when it hits the crown of the trees. Then you might see a decrease. Then you might see another sort of peak as it sort of interacts with the understory, and then a decrease energy. And then finally, if that pulse hits the ground, you'd see a final peak. And so this is basically like a full distribution on the energy, and you get much more information about the forest this way, as opposed to single discrete returns. So this is great for the forestry research community. The problem is most people don't want to work with waveforms. It's kind of a difficult thing. They don't want to have to pick out their own elevation. Ultimately, they just want an X, Y, and Z value on the ground or at a certain amount of locations. So most modern LiDARs are actually probably flying full waveform LiDARs, but what they return to the users is they pick out discrete returns. Excuse me. So they'll pick out this as sort of the top of the tree, and they'll pick out some mid-story points, and then they'll pick out a ground return, and they'll do it sort of post-processing. But the actual collects all that information, and then they can subset what they provide to their users. So some of the newer campaigns that are out there that are using full waveform are NASA's JEDI mission, which is on the International Space Station, and ISAT-1, which was a studied polar ice caps. That was a full waveform LiDAR mission. So these LiDAR collections are pretty complicated, as we talked about, but also the data processing is also pretty complicated, and there's a lot of errors associated in each component, which is important to keep in mind. So one of the biggest sources of uncertainty is the GPS and the IMU, like processing the trajectory of the plane, how that plane was bouncing around in space. But there's also things to consider like calibration and mounting parameters. So you have to remember these are actually like, discrete instruments that are mounted on the plane. And depending on your aircraft, you might not have the ability to mount them right next to each other. Your IMU might be in a different location on your GPS. And so you have to measure all these lever arms to make sure everything is, properly calibrated and mounted properly, and you know the distances to everything. In addition to your actual raw LiDAR measurement, which is actually that height measurement and the angle of the laser, all of these things come together in post-processing to ultimately produce an X, Y, and Z on the ground in a single reference frame. So remember, these are all different reference frames that have to come together to put a georeferenced XYZ in the end. And unfortunately, there are other things that are sometimes out of your control that contribute to these uncertainties. These are things like weather, vegetation, and the terrain itself. So this was a big problem with radar altimeters because I mentioned that big footprint. And if you were measuring something on slopes, like slope of the ice sheet, that footprint gets spread out. And so you get a lot of sort of errors because you're averaging all of this data from this large slope. To come up with an accurate elevation was difficult, which is why LiDARs were a little bit more preferable, especially in high slope areas, because that smaller footprint performs much more. You're not as averaging as much over a large sloped area. But basically, the bottom line here is always be aware of uncertainties and errors. And if you see anything funny, it's always important to look at sort of the metadata or survey reports to see how the data was processed, if there were any issues in the processing, or if they quantified what some of the errors were during the processing. So now I'm going to pass it to Chris, who's going to talk a little bit about structure from motion.
Thanks, Matt. Yeah, so this is just a bit of a brief interlude because this presentation webinar this week is about point clouds, and it's worth mentioning that although Matt just gave you a nice overview of LiDAR, which is the primary technology still used for high resolution topographic surveying, there's been a considerable amount of advancing in the sort of photogrammetric world to produce very similar looking data products. So many of you may have heard this thing called structure from motion, which has its origins in the kind of computer vision world in the 70s, but really has become far more common and approachable in the last decade or two, largely due to just increased compute power. And the way this works is unlike traditional photogrammetry, where you need to understand the position of the aircraft and the camera parameters, but for the images that are collected. So those of you that use a stereoscope and mapped in 3 dimensions on aerial photography, maybe you did this years ago in a class or something. In school, structure from motion doesn't really require the same constraints in terms of the collection geometry or this camera itself. But it's essentially a photogrammetric technique that takes a whole series of 2D images that overlap each other to construct a 3D model. And that constructs the scene, which is basically the topography or whatever the camera is taking pictures of, as well as actually back calculates the camera locations and the camera parameters, so like the lens parameters for the cameras. It's sometimes when you actually do this processing, it seems a little bit like magic that this actually works, but it does. And what it does is it's taking advantage of overlapping images that have the same features in them. So basically identifying pixels that are from the same features. So the same bush on the ground in this example of along a earthquake ground rupture in northern Mexico. and uses those matched positions to essentially triangulate and construct these 3D very dense point clouds. Um, and we're not going to go into this in much detail today. We just don't have time. But I just wanted to point out that we have in the past done whole short courses on structure for motion photogrammetry. So if you go to the OpenTopography website, I'll toss the links in the chat. I'm trying to see the chat with other content that's been mentioned. You can watch we have whole lectures on how this works and demo data sets to do the data processing yourself. It is typically in the world that we live in sort of done with a camera mounted on a drone or a balloon. But you can do it with a handheld camera pointed at, like, say, a rock outcrop or a boulder in your backyard or whatever. Um, and it takes some practice to get it right, to figure out this collection geometry that get the photos overlapped correctly, but it is quite powerful. And so, Matt, next slide. So when we think about these kinds of high resolution topographic data sets, Matt was talking about Lidar, specifically Lidar on airplanes, but also terrestrial laser scanning is a tool that gets used for kind of earth science applications, that sort of site specific locations. So that's the sort of left side of this slide. On the right side is structure for motion. And so typically we put a camera, and it can be a relatively cheap, affordable camera, on either a drone, which also now currently you can buy a low cost UAS system. Or if you don't want to deal with sort of the regulatory framework around UAVs, you can also hang a camera off a balloon or something like that. And so we've done a fair amount of work with helium-filled balloons with cameras hanging off the bottom of them. And that's another interesting way to collect this kind of imagery. There's sort of significant differences in these two sets of technologies, but ultimately the data products come out looking pretty similar in the sense that you get these kind of very dense point cloud data sets that Matt's going to talk more about for the rest of this webinar. But you come at it from very different places. So, laser scanners are very expensive. A laser scanner on an aircraft is millions of dollars, not to mention the cost of the plane. You can buy a UAV now for hundreds of dollars that has a camera on it that will essentially allow you to create very similar looking data sets. There are some important other differences, though. Lidar, because of the multi-return capability Matt was just talking about, allows you to penetrate vegetation. So conceptually, you can see through the trees and get returns off of the ground surface below the trees. This does not work with photography. If the photograph doesn't have the ground in it, you're not going to get the ground. So this is a better tool for sort of more arid landscapes where there isn't a lot of vegetation. And the other thing that the structure for motion approach gives you is color. So because you're using photographs that have RGB color values associated with them, every point has a color associated with it. So that image in the previous slide looks photorealistic because it's inherently just getting the color attributes from the optical imagery. Whereas LiDAR data, Matt will show you some examples, I think, later when he does the demo, color RGB color is not native to the laser scanner. The laser scanner sees the world in like the near infrared. So if you want colorized point cloud with a laser scanner, you have to also collect imagery, and then you have to kind of fuse the two. So that's an important distinction. And they both have their, as Matt talked about, errors and error sources. There are things to be aware of. We won't delve into this, but well collected SFM data, well with good external ground control, survey benchmarks, et cetera, can be quite good and quite powerful and much, much lower cost than airborne laser scanning. So the other thing to say about this technology before I hand back to Matt is that you can, as I said, you can do this with handheld photographs. You can also do it with archival imagery. So people have gone back to old aerial photography collected decades ago and run it through the SFM workflow and constructed topographic models based on historic archived imagery. So if you work in a place where there isn't LiDAR, but you have access to, say, old aerial photography, this is also something worth exploring. So I think that's all I'll say here, and I'll encourage you to I'll encourage you to look at those webinars, which I'll put in the chat. So thanks.
Yeah, thanks, Chris. Yeah, structure for motion stuff is really interesting, and we do have a fair amount of structure for motion data within OpenTopography. So I'm just going to talk a little bit about data file formats because there's a variety of formats out there. The point cloud is a fundamental Lidar output and a file format. It's a true 3D format in that it's a X, Y, and Z for all points. Um, and sometimes there are sort of attributes, a variety of attributes associated with each of those points. So you might have a return number, classification value, GPS timestamp, things like that. Um, the primary sort of uh, point cloud format is LAS, which was developed by the American Society for Photogrammetry and Remote Sensing, ASPRS. They came up with this format and they maintain it and sort of keep it updated. But I do want to put a plug-in for the LAZ form of this format. So this is LAZ is basically just a highly compressed LAS data format. It was developed by Martin Eisenberg, who created the very popular program called LastTools. Um, I've seen really high I mean, I've seen LAZs be like 10% of what an LAS is. So it really compresses quite nicely. This also depends on how the data set is organized. If it's organized properly, it can compress a lot better. Um, but there are other sort of new formats coming out. There's one called COPSI, which stands for Cloud Optimized Point Cloud. This is like sort of a cloud optimized GeoTIFF that we'll talk about next week with rasters. And then there's the Entwine format. Both of these formats were sort of cloud optimized. They were developed initially to help with like a sort of web visualization of point clouds because you can imagine there's a lot of data. And so how do you visualize this data efficiently through a web browser interface, which is what we're going to do during the demo. And so these are sort of like Octree based data formats optimized for the web. One last one that's more so with like satellite missions, like NASA and NOAA's satellite altimeters. They'll put out data sets in HDF5. Um, I don't think we have any HDF5 data sets in OpenTopography, but at OpenTopography, we allow, regardless of how the data comes into us, we allow users to export in three formats: LAS, LAZ, or ASCII. We sort of discourage ASCII because of the size of some of these data sets. Those file sizes get quite large and you'd be limited in terms of your job size. But it is a useful tool for like education and things. So we've kept it around as an output, a potential output format. So this slide is super dry, but I always keep it in because I feel it's important and maybe it's dear to my heart because I deal with last headers all the time. And I feel like you can learn a lot about the data set without even looking at it graphically or plotting it. Just by looking at the headers, you can do a lot of troubleshooting with the data set. So most tools like LastTools or PDAL will have some option of being able to look at these headers, and you can get things like you can see if the file's empty. You can see if there's point counts. You can see what version of LAS it's using. You can even see if it's one of the common problems is this data projected or is it in a geographic coordinate system? You could see that by just looking at the last headers because you can get, the min X, Y, and Z, max X, Y, and Z. You can get a feel for the classification. So if you're ever troubleshooting anything, I always encourage users to look at the last file headers. As Chris mentioned, you can often have colorized point clouds. Now with a LiDAR collect, an airborne LiDAR collect, you'd have to have imagery taken at the same time to be able to do this. And you can colorize each XYZ with an red, green, and blue, an RGB value for each point. So this image here on the right is from the Dangerman Preserve in California, and it's colored. They took ortho imagery at the same time as a LiDAR collect, and so each one of this is actually points, not an image. These are actually XYZ points colored by the ortho photos. As Chris mentioned, one of the benefits of structure from motion is this is sort of already baked into the process. So you're creating your point cloud from the imagery, and so you already have those colorized points. So that's kind of a nice feature of structure from motion. Another thing to mention is that this can be done asynchronously. It doesn't have to be imagery at the same time. It's just you have to be a little careful if you're running this in an area where there's a lot of change. You can get some weird effects if you're applying like imagery from a later date or an earlier date to a LiDAR collection. For example, one thing I see a lot is like pavement colored cars. So like when the LiDAR came, there was a car there, but then when the imagery came, there was no car there, and so you get these weird kind of artifacts. Um, but it's still a cool thing to do, and it really helps with the visualization. We have one of our interns a couple years ago did created a great notebook where he uses NAPE imagery, National Agricultural Imagery Program. They have imagery across the whole US, and you can use that to sort of colorize 3D USGS point clouds. So I encourage you, if you're interested in this process, we have his notebook in our OpenTopography GitHub repo. You can check that out. Most people are familiar with point cloud classifications, but if not, it's sort of used to be a very manual process where technicians would go in and sort of select points and say, this is vegetation, this is ground, this is water. As geoscientists, most people are interested in bare earth, but there's a lot of other classifications out there. Different types of water. Vegetation is even broken down generally into low, middle, and high. I should mention that OpenTopography, we don't reclassify our data currently. So however the data is provided to us from our data providers, that's what we supply to the user. Um, we are thinking about maybe coming up with a tool where you can sort of reclassify stuff, but that's still in the works. And the other thing I want to mention is that the ASPRS is actually maintaining this, and they're coming up with new classifications, particularly in the field of bathymetry. There weren't a lot of standardized bathymetry classifications, and so they're working on that to come up with things like, is there a structure at the bottom of the shallow sea? Is there a structure suspended in the water column? And there would be classifications for all of those types of things. But you can imagine this is a very manual process, but this is a perfect sort of use case for sort of machine learning and AI. And that's sort of what we're seeing now. You see a lot of these classifications is more using these sort of intelligent algorithms to come up with that. And one of the fields where there's been a lot of advancement to this is autonomous driving, because you can imagine it's a safety issue. It's very important for them to be able to quickly real-time identification of something. If that platform, in this case, a car, is moving along, the sensor has to be able to identify, is this a person? Is this another car? Is this a wall? Or is this just a leaf blowing in front of the car? So there's been a lot of advancement in this field from autonomous driving or autonomous vehicles. Um, the problem is interesting to me because from a geoscience perspective, we always want more data, more data, more data. And more data is better. Mapping, characterizing the surface, you want as much data as you can. With autonomous vehicles, because they have so much data coming in and at such a fast rate, they actually have to thin their data down just to the bare amount so that they can identify something accurately. So they're trying to straddle that sweet spot of like just enough data to be able to identify something accurately, because they can't handle all of those data volumes. It would just bog the system down. So it's sort of like a switch on our problem of wanting more data. They want just enough data, not too much. So at OpenTopography, we try to create this platform that makes it easy for users to access this data, which can be difficult to work with. It's based on a lot of open source tools. But a lot of times people just want to work on stuff themselves. They want to download the bulk data and maybe do their own thing. And I'll show you how to do that a little later. But I just wanted to point out some of the tools that not only OpenTopography is using, but also is available to the community. The two big players in the LiDAR field are Rapid Lasso's LASS tools that was developed by Martin Eisenberg, and PDAL. So these are used by OpenTopography, but they're also available to anybody. PDAL is very powerful. It's command line driven. So if you're not too comfortable with the command line, it could be a bit of a learning curve with it. LASS tools is more Windows based. It has a GUI. It's a little flaky, but it also has a command line as well. But both of these tools are very powerful, and you can do a lot of things with them. There's also Cloud Compare, which has a GUI and is really easy to use. In fact, we have a whole webinar about how to use Cloud Compare. So if you go to our YouTube channel, you'll see a whole webinar dedicated to using Cloud Compare. Newer versions of QGIS allow import of LiDAR point clouds and visualization. So that's really been really useful and handy. If you're comfortable with sort of coding, there's a lot of libraries out there. Just a couple here I'll mention is LastPy um, has a lot of capabilities. PDAL actually has an API where you can use all the PDAL command lines within Python code. And Whitebox Tools also has a lot of features for working with Lidar. And then just lastly, this Class.io is a cool visualizer. So it's using the same kind of Potree 3D demo that I'm going to show in a little bit, but it's a standalone URL, so you can just like upload your point cloud file and visualize it with sort of some standard tools. So these are all sort of good options for anyone that's interested in just looking at stuff on their own. So I'm going to get out of sharing mode now and just sort of do a little demo about some of the features at OpenTopo. We'll look at landing pages and how to access point cloud data. Then we'll do a little bit of a deeper dive into the 3D visualizer. It's also called Potree. It's sort of not intuitive, so it'll be, well, there are bits of it that are not intuitive, so it'll be good to do a demo about it. And then lastly, we'll talk about bulk access and how to access data without going through the OpenTopography portal. So being able to download the raw tiled LiDAR data sets on your own. So let me stop sharing. Okay, hopefully you can all see my browser. Um, and I just want to clarify something I mentioned last week. I sort of misspoke a bit about this search OpenTopography toolbar. I was trying to discourage users from entering a lat long coordinate in there. Some people were trying to look for data and they were just hitting the going to the search bar, entering a lat long. But you can search for like terms. So like let's say I want to look at these Gisborne data set. So if you know like a keyword term, you can put it in there and it'll return um, data if it finds it. If it wants to find like web content, you can click the search site content, and this will show you any kind of news items or blog posts or other things that are related to that keyword that you typed in. So here I wanted to look at this data set because this is one of our Land Information New Zealand data sets that has RGB values associated with it. So this is what we call the sort of landing page. This is sort of the main page that has all the metadata. This is sort of like the top level of for data collection. And I'm just going to highlight some of the more important parts of it and just walk through it, and then we'll talk through running a point cloud job. One of the key components is every data set in OpenTopography gets a digital object identifier, DOI. This is a persistent URL so that even if we change things on the background, if you always use this URL, it'll always return to this landing page. So this is really important for citations. And in fact, we include it in the citations here. So here you can see if ever you use this data set and you want to publish something, you can put this citation in there. Instead of putting us in the acknowledgement, we prefer if you'd actually cite the data. And that data would include that DOI so that users can always come back to this landing page. So here we have the buttons for accessing the point cloud data. If this data set had rasters that we hosted, you'd see a little raster button. The Land Information New Zealand is a little unique in that they do have rasters, but they're hosted by a separate organization. So the rasters in this case are have links here that goes to an external resource. But if we are hosting, OpenTopography is hosting the rasters, you'd see a little raster button here, and we'll talk about that next week. I'll show those differences. So we have a description about the data, some logos, again, the citation, which is really important, collection dates, funders, partners, collectors, any kind of attribution, we like to make sure that that gets properly attributed. Then there'll be some stats about the data set, which is really useful to have. And then at the bottom, there'll be a link to the survey report. As I mentioned on that one data processing slide, this is really useful. If you see any anomalies in the data, you might want to check that out to see if there are any issues while they were collecting it. It will report maybe uncertainties or other things. But another really useful feature is this last validation reports. So if you click on that, as part of our ingest, we do a whole QA/QC on the data. And so you can sort of see a bunch of stats about the data sets, the number of files, the breakdown of classifications, the projections, different things. But one of the more useful ones is we actually do a comparison of what's reported in the headers versus doing an actual scan and calculation ourselves. Because sometimes there'll be some differences between what's reported in the header versus what's actually calculated. So here's the header information, and here's the results from our file scan. And so this is actually going through all the component tiled LiDAR files that are on the back end, and doing stats in the min-max XYZs, areas, point densities. So this is another good, useful tool for any kind of troubleshooting. If you see any anomalies in any of the data sets, and you can compare it maybe to what the headers are showing to see if there's any differences. So I just wanted to point that out. Not a lot of people sort of know about that, but it's a really useful tool. We produce a tile index in a shapefile format, and I'll talk about that when we talk about the bulk in a little bit. And then we also have links to all the boundaries. So if you want to pull the boundary of this data set into GeoGIS, you can download these are GeoJSON vector files. So that's the basics of the landing page. If you go to run a job, you would click this point cloud data. And you could just think of this as like a sub page. So like at the top level, you have the landing page, and then below that you have either a raster page or a point cloud data page. The reason we break it out differently is because sometimes there's differences because they're different products. But basically, it's a lot of the same information. So this is the point cloud data page. You have links back to the landing page here. If you were going to run a job, you would just click select a region, and then you would just sort of draw a box. You can change the base map here if you wanted to. It'll pull in imagery. Here I selected a large area, so it'll give you a warning if you selected too large of an area, and it gives an estimate of how many points will be in that job. If you do have the coordinates are in the local or in the coordinate system of the data set. So in this case, they're in this New Zealand UTM based sort of horizontal coordinate system. You can always, if you knew the coordinates that you wanted, you can manually enter them if you want to. You could also filter by classification. As I mentioned, these are classifications as they're supplied to us. So you can filter by buildings, ground, unclassified vegetation, water surface. You can exclude noise. I would generally always exclude noise unless you had a certain reason. This will exclude both low and high noise, so it's kind of nice. And some data sets have a fair amount of noise, so it's probably good to filter that out. As I mentioned, you can output in a variety of formats, LAZ, LAS, or ASCII. We have LAZ as a default, and I would recommend that you keep it that way. It's a really useful format. Next two stages, I won't talk about too much because we're going to talk about them next week when we talk about rasters. So these are the gridding operations. So this is actually gridding, creating a raster DEM from the raw point cloud, and these are the parameters that you would use to do that. But we'll talk about that next week when we talk about interpolations and gridding. We have a raster visualization where you can visualize those rasters that you just created. Excuse me. There's this 3D point cloud visualization, which is what we're going to talk about in a bit. So if you select that, when the job is finished, you'll get a little link. You can click on that, and it'll open the visualization, 3D visualizer. You can create contour lines. So with contour lines for LiDAR, it can be a little tricky because LiDAR is so sensitive, picks up a lot of different things, and is, picks up high res features that if you produce contours directly from the gridded LiDAR, it'll be very noisy, very jagged. So a lot of people don't like that. So what we offer is the opportunity to smooth the data a little bit so that you can get these nice smooth contours. Obviously, if you don't want that, there's an option. You can select 0, no smoothing. This will not smooth your input DEM at all. It'll produce contours directly from the gridded product. But it generally is better to smooth the data a little bit just to get these nice smooth contours. You have a variety of contour levels to choose from, everything from 10 centimeters to 100 meters. And you can output in shapefile DXF, which is good for CAD programs, and GeoPackage. And then lastly, there's this Tau DEM. This is basically like Arc Hydro tools, if people are familiar with the Esri products Hydro tools. This will create things like pit-filled DEMs, flow direction models. You can create drainage basins, stream networks. This runs on a supercomputer at the San Diego Supercomputing Center, and it's useful for any kind of hydrologic applications you may have. So lastly, you just need to put in your email, and you can put in a title for your job or a description. It's basically for you for your purposes. And then when you hit submit, the job gets run on our high performance computing at San Diego Supercomputing Center. Um, if it's a small job, it'll take, a couple seconds. You can just wait. But if it's a longer job, um, you can go do something else and you'll get an email when it's finished with links to download the products. And so I won't run this job here. I have one saved somewhere. Here we go. So I get an email. I can show you what the email looks like. So this would be the email I got, and you just get a link to that job. You click on that link, and you'll have links to download the products that you selected. So here's your Aurora point cloud, here's your gridded tins, here's your visualization, the contours, and then any kind of visualization products that are underneath. So that's the basics of sort of running a point cloud job and how to get your output products. Now we're gonna jump into doing the 3D visualizer and looking at how to visualize the point cloud in 3D. So that's this link here. So this was in that job. We had selected this part here, generate 3D point cloud. That produced this link. So we're going to open that up. And the beauty of this is you don't need install any software or anything. It's all browser driven. And this is what I was talking about earlier with the web optimized point cloud formats. This really helps. So this is actually visualizing the point cloud. So you could see if it was loading all data all the time, it would be really slow. But it's pretty fast considering it's millions and millions of points. So there's a couple little flaky things with this Potree viewer I want to point out. I'd encourage users just to try it out, play with it. If you have any questions, always reach out to us. Some things are not super intuitive. The first thing is you might not see any menus. You have to click in this upper left corner. If you click this little 3 horizontal lines, you'll get the menu. There's a ton of menus here. It can be a little overwhelming. Some of the things I just wanted to point out is like the point budget, depending on your laptop. If this is all maxed out, it might be a little slow. So you can sort of thin the data with that slider there. There's a couple lighting options, which are nice. So there's this iDome lighting. So right now it's enabled, but if you turned off, you see it, you get a different look. I like to keep it on. I think the shading really helps pick out features. You could see the trees are definitely more identifiable with the iDome lighting. One of the main things that I use, and I just wanted to point out, is that you can change the attributes that you're actually viewing. So here we're viewing elevation. You can change the color scales. But the reason I chose this data set is it has RGBs. So here is a red, green, and blue because they took ortho imagery at the same time as the Lidar collect. And so now we have a sort of a photorealistic point cloud. And you can see it almost looks like a picture. You can see this is like a lumber yard. And so you can change the attribute that you're actually plotting. So you can do things like, let's look at intensity. So this is like intensity, and you can change the range to sort of see the intensity of those for each point, what's coming back. So it's really nice. You can do classification is a useful one. So obviously they were smart and they made water blue and vegetation is green, buildings are orange. So you can plot by different parameters here. So we'll keep it on RGB. I'll talk a little bit about filters. This is another useful thing that I use a lot. So you can just filter by whatever classifications are in that data set. turn the buildings off, you can see the buildings disappear. This data set just happens to have vegetation broken into low, medium, and high. And so that's really nice. You can see as I click down, you can see the vegetation going away. Water, you can turn water on and off. So it's kind of nice way of filtering the data. You can also filter by returns. Let's say you just wanted the first return, you can do that. And so one other thing I want to talk about that it could be a little tricky, but is really useful is the tool sets that are in this Potree viewer. So if you click on the tools, it expands this other menu. And you can see there's a variety of tools here. There's one for point measurement. And here, as I'm moving this point, it's snapping to any sort of LiDAR point, and it's giving me sort of the X, Y, and Z of that point. So this is a really kind of cool feature just to sort of spot check any kind of files or any kind of points on the map to see what their XYZ is. You have things like distance measurement. So here we can measure like the length of this ship. And here's what's a little tricky. And a lot of it depends. I'm on a Mac with a trackpad, so it behaves a little differently. Sometimes it's a little better if you have an external mouse. But here, if you left click and then left click and drag, and then right click to end. And so it just measured that ship as 179 meters. The last tool I'm going to mention, this one tends to be a little flaky. So let's see what happens. And I encourage users to try it out, but it is pretty useful, is this profile tool. So it's a height profile tool. So if you click on this, and let's say we'll start here, just go up here, and then you right click to end, and you'll see that nothing happens. So it's a little unintuitive to users. What you have to do is you have to scroll down, and you'll see this show 2D profile button. So if you click on that, it should in theory show you the profile. Now, right before I was doing this demo, I was trying this out and it was acting flaky. Sometimes you need to just like start it fresh. So like let's open it up again. And let's try it again. So again, we're going to open up our menus. We're going to go to tools, go to height profile, and we're going to start from here. And we're going to go, oops, do it again. And we go there, right click, show you 2D profile. So if we zoom out, it might be hard to see, but I have this red line here. And as I move along the profile, you should see that little beach ball sort of showing the position of my profile along that on the map. You could also change the width of the profile. You see how there's a little bit of a red line to the width. You can make it like 1 pixel wide or 1 meter wide. And this is sort of just a nice way of profiling data. It's a little flaky, so you got to play with it, but it's kind of useful to have. So I think that's gonna stop there with the 3D Potree viewer. I'm gonna transition into sort of bulk downloads because I want to leave some time for questions. So let's get out of this. And I'm gonna go back to the data catalog. And I'm just gonna look at one of these smaller data sets here. So as I mentioned, there's going to be a couple ways to bulk download data from OpenTopo. You can see there's this bulk download button on any page. You click on that, and it's going to give you this sort of text here. And this is basically explaining 3 different ways to get the bulk download. If you're comfortable with the command line, you can use the AWS command line tools. So we have the commands provided here where you can list the data in the buckets, or you can just download specific or all the buckets, all the data sets within a bucket. So those 2 commands are there using the AWS command line tools. If you're not comfortable with the command line, you can use a program called CyberDuck. It's a free program that used to be for like FTP access, but it handles a bunch of different protocols, including Amazon S3 buckets. So we have the parameters there of how you'd sign in, create a profile in Cyberduck to download the data. If you're not comfortable with that, there's a third option where you can select this agree and access data button. This will take you to this MinIO browser. And this is basically just a browser-based way of seeing all the files that are on the back end of this collection. And you can select the actual files that you want. You can search for a file name. You can select all of them, but a lot of these collections have thousands of files, so that could be difficult. But then if you select this download all as zip, it'll zip up all the files that you selected and then prompt you to download it. And one thing that sometimes confuses users is if you select a lot of files, it doesn't give you a progress bar, unfortunately. So it'll take some time to create that zip. You just got to keep this window open, and then eventually you'll get a pop-up saying, where do you want to save this files to? So that's bulk access, turn a traditional sort of bulk access. The last thing I'm going to mention is tile indexes and how to access bulk data through tile indexes. So I mentioned for each data set, we create a tile index. It's in the shapefile format, a zipped shapefile. So if you download that and pull it into a GIS, let's see, you'd see something like this. It's basically showing the spatial boundaries of each of those tiles. So if you zoom in, this is in QGIS, this is the shapefile. And if I use the info tool, which is very similar to the ArcMap info tool, and you click on a tile, it's going to give you the attribute table for that tile. And it gives you basic information like min and max, X, Y, and Z. But the critical piece here is it gives you the URL directly to that Lidar tile. So if you click on that, it'll prompt you to download it locally to your machine. So this is just sort of a nice way of pulling it in because then you have the context of a base map where you're in your own GIS. Ultimately, we prefer if users just use OpenTopography because we're doing all this heavy lifting on the back end, we're mosaicing all the products and doing all these things for you. But ultimately, if you wanted to mess with the tiles yourself, those are a couple different ways that you can do it yourself, pulling in those tiles. So that's basically all I had for the point clouds. I wanted to leave some time for questions. I'm sorry I went a little over, but I'm going to stop. I want to leave this slide up. I don't know in case people need it.
Great. Thanks, Matt. We've been sort of picking off questions as we go, so hopefully people have been keeping an eye on the answered tab in the Q&A. So just a quick review. I won't reiterate exactly, but there were a couple of good questions about digital elevation models and digital elevation model types, and also on topographic differencing. So those are topics to be covered in the coming 2 webinars. So come back next Wednesday and the Wednesday after, or check the YouTube recordings if you're interested in those topics. We'll do a much deeper dive on both of those. Chelsea clarified a couple questions about coordinate systems and coordinates for data sets. And then we got 2 kind of open questions that are, one is Matt, bathymetric LiDAR. Technology limitations. Can you say a little bit more about this bathy data?
Yeah, I don't know. I didn't work with bathymetry data much. Some of the sensors we work with, I mean, the only limitation I know is like, it can't. There are depth limitations and limitations of like the water quality. Like it really won't perform well in very muddy waters or things like that. It's going to have issues. And I can't really speak too much about the different technologies, but I do know like ICESat-2 actually has dual lasers on it and it has a bathymetry lidar so that in shallow sections, shallow seas, it's actually getting returns from underneath. But yeah, I think your limitations are really going to be like water quality and depth. Like I don't think you're going to get anything under like over like 50, 100 meters. I think you're pretty limited to shallow seas and shallow water.
Yeah, so these are 532 nanometer green wavelength laser systems. And there's a whole bunch of different sensors out there. that are flown by both commercial vendors as well as some governmental groups like JOBLTEX, which is a U.S. Army Corps of Engineers group that does a lot of coastal surveying. Typically, like near shore bathymetry or inland waterways. So like there's a lot of data, including an OpenTopography, that was collected, for fish habitat studies in the Columbia River Basin, Snake River, places like that. We just posted a data set on the Sacramento River in the central northern California, and that data set has bathymetry as well. So if you're interested in exploring kind of what these data sets can do from a bathymetric sense, the NOAA coastal LiDAR data set in particular, so the blue polygons on the fine data map, a lot of those data sets are topobathy data sets. So they're collected sort of deliberately to map that kind of near shore tidal interface. And so you can go grab some of those data sets and pull them into OpenTopography. Pull them into software and look at them, or use the viewer, the Potree viewer, to look at them. And then the other thing that Chelsea commented, I think somebody else asked, was like, what other, generally the bathymetric data are available. So there are a couple of different these global data sets that are sort of like relatively low resolution, like 500-meter pixels, but have ocean basin bathymetry. So GEBCO is the primary one that's available through OpenTopography, but there's also an SRTM 15 plus, I think is the name of that data set, that also has bathymetry. So obviously the quality of bathymetry in the deep oceans is much, much lower and is all collected from boat-based multi-beam sonar types of technologies. And then Matt, another question, and people keep throwing them in there at the top of the hour, but we'll hang out for a little while and answer more questions if there are any. Matt, can you just restate the situation with classifications of data sets in OpenTopo?
Yeah, so with the classifications, we generally we do not reclassify currently. So we supply the classifications as they were supplied to us. So that'll vary depending on data provider. Some data providers provide a lot of classifications, some it's very minimal. We are working on potentially having a tool to do some reclassifications, but it's not available yet. The other thing that will come probably sooner than that is we might change our classification filtering options so that right now, like we group things and it was like vegetation, which was a grouping of low, middle, and high vegetation, water buildings. We might expand that out to have like an advanced filtering option where you can like specifically select the classes that you want, and give the user a little bit more finer control over how to filter the data. So that'll probably come before any kind of reclassification. So, but yeah, so right now we're kind of not, I wouldn't say limited because we don't want to mess with the data too much. This is as we don't want to put too much of a fingerprint on the data, and reclassifying the data is certainly putting a fingerprint on the data. So
yeah, a lot of these data sets have been through sort of a QA/QC data acceptance process as part of the contracting. So, a lot of the data sets in OpenTopography, well, basically every data set in OpenTopography, we did not contract the collection of it. We are the host and the distributor of the data. Sometimes the data we're one of many places you get the data. Other times we're the authoritative source. But in general, somebody who has the contract with whoever collected the data sets. So for like the USGS's 3D elevation program, there's a very rigorous QA/QC and data acceptance process where the data have to meet a set of standards that the USGS has defined, and they do that acceptance before the data become publicly acceptable. So our general philosophy has been that we don't want to like start changing things because that makes them essentially different than sort of the state at which they were accepted. There have been exceptions. When things are really messy, we'll fix things. There are some other data sets that have been collected for sort of academic purposes that we've cleaned up. But in general, we try not to muck with the data too much. And then, great, that person asked, follow-on question, are all the data classified? The answer is that the vast majority of data in OpenTopography have a basic set of classifications. So that's typically ground, points that are in the ground class. But it might just be LAS specification class 2, which is ground, or everything else. So like if you want to differentiate trees from buildings, you can't necessarily easily do that. There are some very, very old legacy data sets kind of from the early days of LiDAR and OpenTopography that have no classifications. And that is just the fact of the nature of the early days when these processing tools are not as sophisticated, and data were delivered in ASCII file formats. And so there's some really ugly legacy data out there. But in general, that's kind of where that stands. I guess the other comment is I briefly talked about structure from motion photogrammetry data sets. You can apply a classifier to the photogrammetrically derived data sets, but it is much more complicated because you typically don't have points that represent the ground surface if you're in a densely vegetated environment. So oftentimes these photogrammetrically derived data sets you may find in OpenTopography do not have classifications associated with them. They're just mass points. Cool. Good questions. Jeff asked about APIs. Yeah. So, Jeff, at the moment, we don't have a public facing point cloud API. We have a couple of different APIs. Matt will talk about them next week when we talk about DEMs that will allow you to request gridded elevation data programmatically. We do not have a public facing point cloud API. We do have one internally that we use with specific partners. So if you're really interested in point cloud access via API, you can send us an email and we can talk. But the reason we have not yet pushed out a point cloud API is, I think, as you are alluding to, they're very large data sets. They get very big very quickly. And a lot of these kind of simple RESTful APIs are meant to be relatively quick, not long transit time, long query time, large data volume delivery tools. And so it just doesn't map very well. If you're interested in large volumes of data, the better way to do it is to use the bulk approach that Matt was showing you, either whether that's the tile indexes or going straight to the bulk download interfaces. And we also have, Matt did not talk about it today, but maybe Chelsea, you can dig it up quickly, is the OT 3-dep notebooks. So if you're interested, particularly in USGS 3-dep data, another intern a couple years ago, Cole Speed, built a really nice set of Jupyter notebooks that allow you to go straight to the USGS point cloud data in Amazon Web Services and kind of programmatically process. So build like OpenTopo like processing workflows, but in an entirely programmatic way. And that's directly interacting with sort of cloud native data and is essentially an API kind of interface.
Yeah, I added that link. I've used them. They're very helpful for getting bigger data sets.
Did you put it in okay, it's in the Q&A under answered. Yeah, they've got a bit of a learning curve. Definitely more of an advanced user kind of framework because you have to be familiar with Python and PDAL, but they are spun up in Google Colab, so they're pretty easy to deploy. And Cole's been helpful to keep them maintained. So they're really, if you're looking at larger scale kind of processing workflows, when you start, OpenTopography, for better or worse, does have some practical constraints on the size of the job you can run. If you're bumping into that, these notebooks are really a good way to kind of take your processing to the next level for sort of larger scale analysis. All right. 12:08. There's still some folks hanging out though. So last call for questions if you have any. Otherwise, we'll wrap this up. We will see you all next week, hopefully. Next Wednesday, same time, same place, same Zoom. And in the chat, Chelsea and I have been posting links. So if you missed these webinars or you want to share them with a colleague, please feel free to just send them directly to that YouTube playlist. And then this one I think last week we got it up within, by tomorrow morning kind of timeline. So it should be up relatively soon.
And next week, we'll talk about intro to digital elevation models, and we will touch on the API a little bit next week as well.
Great. Thank you all for coming. Have a good day.
Thank you.